Hello everyone and welcome back to my channel. In this session, I would try to answer some of the very popular questions that was posted on the community, and I would be taking two particular questions in general because that would sort of address a large variety of questions that were actually asked. So in the first part of this video, I would try to mold my simple algorithm code that we had written for the case of lid-driven cavity, and then we would transform it for a pipe flow or a channel flow. So the idea would be how we can use the simple algorithm. So the algorithm remains the same, but how can we adapt it to use or implement it in a channel flow? So usually a channel or a pipe, they are not really a square domain that we had been considering for the lid-driven cavity. So immediately you can see that the geometry of the problem would change. And also, I would implement a different kind of boundary conditions that are called as periodic boundary conditions. In the case of lid-driven cavity, we had been using different kind of velocity boundary conditions, and we saw that if we know about it, we can understand how to implement the pressure boundary conditions as well. But this problem, we are thinking to handle it in a different way. Although there could be velocity and pressure boundary conditions for this case as well, but I want to demo as to how you can utilize or how you can write these kind of codes for the periodic boundary conditions. And in the second part of video, I'll talk a little bit about what is called as a source term. So sometimes in the governing equations, you might have some sort of source term or a sink term that is sitting inside the equation. It could be a thermal source, it could be a momentum source, or it could be a body force, for instance. So I would give you a glimpse of how you can handle that when it comes to discretizing the equation. And because this is an introductory course, I don't want to dive in very deep into that because that would need another lecture or so. So let's get started with the first part of this problem. What you see on the screen is a code that I have modified using the previous code for the lid-driven cavity, and now this code can solve for the channel flow using the periodic boundary conditions. So I'll highlight some of the things that I've changed as compared to the past code. So the first thing, as I mentioned previously, was regarding the geometry of the problem domain. So rather than having endpoints the same value for both x and y direction, which is typically of a square domain, I'm defining endpoints y, that is in the vertical direction, and endpoints x, that is in the horizontal direction. So this number would also determine what my domain lengths would be. So this is what I'm talking about, the physical geometry of the problem. So we are assuming that a pipe or a channel which is 10 meter long or 10 units long and it's 1 unit high. And the next thing that I'm saying is that the edge or the grid spacing can be obtained from either of these two, and we are assuming that it's a uniform grid. So even though the geometry is, you can say it's non-square, but we are assuming that the grid is a square grid. So we are not taking into account the rectangularity or non-linearity or non-uniformity of the grid. So we are sticking with the uniform grid that we had been using so far, so that it doesn't become too complicated for you. So once we define the grid spacing, we can define what are the x and the y grid points. So very similar to what we had been doing. And also similar to the case of a lid-driven cavity, I define the kinematic viscosity, or sort of a representation of a Reynolds number that appears in the momentum equation. My non-dimensionalized density is 1 and my under relaxation factors are 0.1 and 0.8. And depending on the non-linearity of the problem, or depending on how high the Reynolds number is, you can change these factors. If the Reynolds number is very high, it may not work with the same factors and you might have to reduce it. The initialization of the variables is pretty much the same. So we have some variables that we want to store in the collocated grid as the final solution, and we have some staggered variables that we have been typically using. So a slight difference that you'll observe at a later point might be regarding the boundary condition. So at first here, I have given some boundary conditions here for the first row or the first column. So I'll be uploading this code on the Google Drive where all the other codes are uploaded as well, where you can have a look and rather have a deeper look as to what exactly these initialization conditions are. But because we would be using periodic boundary conditions, so you'll see that these initializations wouldn't really matter that much. It would be what we are writing in the boundary condition that would be of much more importance. The first part of the solution loop is very similar to what we have been doing so far. So we call out an error variable, initialize it as 1, call the iterations, initialize that as 0, and our required error is 10 to the power minus 7. Then we initialize a while loop, and that takes care of the error. So it's a conditional statement on the convergence of the solution. So as long as the error is more than the required error, the code would keep producing the output. So first we solve for the x momentum equation, and this is where the indexing of the staggered grid becomes important. So this is something, if you don't really understand very well, please go back to the previous lecture where we talked about the simple algorithm and the led driven cavity, and then come back to this lecture. So the first 4 lines here, they give out the coefficients that we had been using for the different neighbors. So if you don't recall anything, if you remember, the way in which we had obtained the governing equation was in terms of these various coefficients, that is AE, AW, AN and AS. So that's exactly what I have written over here, that they are the coefficient of the neighboring grid points. And based on that, we can define the coefficient of the grid point in focus, that is AP. So once we have AP, the next term is DU, which is sort of equivalent to DE that we have been using in the previous formulations. So it is a term that we need for accounting the pressure. So this is the coefficient of that particular term. And later on, we use it for the pressure field. So here, rather than writing in terms of DU, I've simply multiplied it in terms of H. So this DU, mind you that this is also used in the continuity equation over here. So this is where we would be using those DU and probably DV. I've written it in that particular fashion. So this is something that we have looked in the lid driven cavity problem, and this is exactly the same. There is no change in the U momentum equation, at least for the interior of the domain. So this was just a recap, and now I want to focus on the main thing, that is the periodic boundary condition. So let us first try to understand what this boundary condition really is. So sometimes it might happen that, for example, you are given the velocity, let us say U velocity on the left face, then you can simply write that the velocities that are lying on the face, such as these velocities here, let me quickly draw it for you. So if we are talking about some velocities like these, because the velocity at this face is specified, so we can directly give out the values. Sometimes the velocity gradient is specified, so we might have to do some calculations and then use that boundary condition. The periodic boundary condition means that the domain is periodic. So you can imagine that if you have, let us say, this size of domain, the periodic boundary condition says that whatever is going out of here, it's coming into the domain from the other end. So this is a 1D representation of a periodic boundary. So in this case, we can assume that if the flow is fully developed, or if the flow is laminar and fully developed, then there are no changes in the velocity field in the x direction, and there are only changes in the y direction. So you have to go back to your fluid mechanics textbook and remind yourself of that. So in that case, we can assume that the flow is periodic as well in a computational sense. So we can say that whatever the U velocity is going from this end, it is exactly the same as coming in this end. So it's like keeping these infinite number of pipes in your domain, but it is important that it is only in the x direction. In the y direction, there are changes, there is a boundary layer that develops, and there is no slip boundary conditions on the top and the bottom wall. So we would be using periodic boundary condition in x, whereas the no slip boundary conditions in the y direction. So to implement the periodic boundary condition, the idea is very simple. So the unknown velocity is here. In that case, it's the left face velocity and the right face velocity. So what we say according to the periodic boundary condition is, you can imagine that you take this particular section here of the domain and you simply put it on the top of this domain here on the right side. So you can imagine that when you put it on the top of each other, what happens is that the first column, it would coincide with the second last column, and similarly the second column would coincide with the last column. And that is what we use for giving out the boundary condition in the code. We say that take the values of the first column same as the second last column, and take the last column, which is unknown, as the second column. So the second column and the second last column, these are the known values, whereas the first and the last column, those are the unknown values. So that's the funda behind implementing the periodic boundary condition. So you just take the domain, chip it on the top of each other, and you can see that the first column coincides with the second last, and the last column coincides with the second column. And that is exactly what I'm writing in the boundary statements over here. I'm saying that the first column, it's exactly equal to the last column here, and the last column, it's the second last column, and the last column here, it's equivalent or it's exactly equal to the second column. And because we are trying to use the no slip boundary conditions on the top and bottom wall, so that is exactly the same as the lid-driven cavity case, where we said that if the boundary is lying in between, the average of these two velocities, that should be equals to 0. And if this is a no slip boundary, that means that these two velocities, they should be negative of each other. So we are writing that the first row, it's the negative of the second row, and similarly the last row, it's the negative of the second last row. Similarly, we do it for the V momentum equation or the Y momentum equation. This particular part is exactly the same. So we define the coefficients, we calculate the V star, we under relax it, and that's exactly the same for the channel flow case as it was for the lid driven cavity. The only difference is again for the velocity boundary condition, and we again use the same idea that we have a flow that is periodic in X domain. So what first we do is, because the top boundary is a no slip boundary condition, and recall that the V velocity, it lies on the top boundary and the bottom boundary as indicated by these green arrows. So we can simply assign those particular V velocities as 0. The difference would lie here in these two lines, where again we would say that the first column, it's equivalent to the second last column, and the second column, it's equivalent to the last column. So that's what I am writing here, that this is the first column and this is exactly equal to the second last column. And mind you that the indexing here, the second last column corresponds to endpoints x, and endpoints x plus 1, that corresponds to the last column. So remember how the staggering for the u and v velocities were different. They had different number of rows and columns. So take care of that while writing the code. The final part was about solving the continuity equation, in which there is again no changes at all. So we are using the pressure corrections. So we start the pressure corrections as 0, then we solve the continuity equation for the pressure corrections. We use these corrections to update the pressure field, and after that we can use some sort of boundary conditions according to the problem. So here, because we are using the periodic boundary conditions, the pressure information itself, it becomes of not much use. So the pressure boundary conditions are not really needed, because those particular boundary points, they don't really get into our calculation because we are using this periodic boundary condition. So the boundary conditions have to be taken care of very carefully if there are different kind of boundary conditions, but we are lucky that in this case the pressure boundary condition won't affect the solution. Finally, after getting the pressure corrections, I update the velocity field. I get my u new using the u star and the pressure corrections, and again I implement the same boundary conditions on the u new field. So first I updated the u star and then implemented the boundary conditions there. Then I updated the u new using these pressure corrections and then implemented the boundary conditions again. So the idea is whenever you update your velocity or the pressure field or any field, implement the boundary conditions as well. You can do it one before the other, that doesn't really matter, but you have to do it. Otherwise, there might be problems whenever you would proceed with a different time step. And similarly, I do it for the velocity field, and again I use the velocity boundary conditions here. Finally, the continuity equation residual is calculated using the Bij, and everything else is the same here. And in the visualization part, I am using two different contours so that you can see the solution, that is U final and P final. I've used a command called as D aspect that sets the aspect ratio of the figure. Otherwise, MATLAB would still plot it as a rectangular figure, so we don't really want that because it's a rectangular pipe, so we want to see how it looks like. So if I run the code, we would be introduced to a similar convergence history plot where the convergence of the solution would be checked with respect to the number of iterations. And finally, once the solution converges, we would get all the plots that we had asked for. So just to quickly give you an overview, this is the vector plot. And if I zoom in here, it's really hard to actually do that because it's a square rectangular plot. So you can see that there are some particular velocity vectors which are very small. So if I zoom in, probably you can see better. So these are, the magnitude is relatively much smaller near the boundary as it should be. And finally, near the center line, we get a higher velocity, which is actually much easier to see in the U velocity contour. So this is the kind of parabolic velocity profile that we expect in linear flow, laminar flow. So the velocity at the center line is maximum, followed by the no slip boundary condition at both the walls. So the periodic boundary conditions implemented that whatever the velocity profile that is going out from the right end, it's exactly the same as what we feed in from the left end. So hopefully that would give you some idea regarding how to implement the periodic boundary condition in a different geometrical configuration. So with this in mind, I hope that you'll be able to tackle different kind of problems where you have different kind of boundary conditions irrespective of the geometry of the problem. If you have been liking the content that I'm providing here, and if you have benefited from it, please consider supporting this channel. You can either subscribe to this channel if you haven't already. Please like the video, and if you can also support me financially through the link shown here, and also it's provided in the description. So now let us move to the second part of this session, where I would talk about the source term linearization. So let us first understand why this source term is important. So I'll consider a diffusion problem just to begin with and to give you an idea. So remember that our diffusion problem was something of this particular form, that we had d square t plus dx square plus d square t over dy square, which is a 2D case, and this was equals to 0. So if we use a finite volume kind of methodology, we can write this particular equation in a very characteristic form that can be given as AP phi p, or in this case actually I would write as APTP equals to AETE plus AWTW plus ANTN plus ASTS. So the purpose of writing this equation in this particular form is that everything that we are unknown, that is on the left hand side, which is TP, that's the whole purpose of writing this equation, and everything that is known to us, it's on the right hand side. So when a source term is introduced in the equation, let us say now we have a source term that is called as S. So the source term linearization says that this S can be broken down as some SC plus some SP times TP. So the source term doesn't has to be a linear term. The original source term, it could be anything. It could be dependent on the variable itself. It could be dependent on some properties, or it could be a constant as well. But the situation becomes a little bit more tricky when, let us say, the source term is dependent on the variable itself. So that is why we introduce this particular term, that is SP times TP. Now, the idea is, however nonlinear the source term is, we don't want to introduce that nonlinearity into our system. The reason is that we had tried very hard to mold that non-linear Navier-Stokes equation into a linear form or a quasi-linear form into through this finite volume methodology. So we had done all this discretization and modeling to get rid of that non-linear term and to model it as a linear operator. But if the source term itself is non-linear, then it would create problems. So what we do is we write that source term, or we try to write that source term in this particular fashion, and we say that if the source term is a linear function of Tp, which is right now is, then we can still use our existing formulation. So we don't have to modify our formulation. And if we write the source term in this particular fashion, the AP term, let us say the new AP term, let us call it AP star, it becomes simply previous AP minus SP. So you can imagine that if we have a source term sitting here, this SP times TP, it would go on the other side and it would appear as a negative of SP. Now, to have a stable numerical scheme, all of these coefficients should ideally be positive. And that is why we postulate that if we have AP minus SP, it might turn out that if the SP is non-zero or it's greater than 0, there is a chance that this AP star, it could be negative, and that could be disastrous. So if you want to really read about it, you can consider any CFD textbook. There is a very good discussion about it in the book of Patankar, and in the 7th chapter where he talks about different kind of finishing touches, and that's a really good module to read. But the idea is, if let us say the SP is negative, so imagine that SP is some negative value, then this difference AP minus SP. So AP was already positive thanks to our formulation, and now if the SP is negative, then AP minus SP would always be positive, and that solves our problem. So we say that SP ideally has always to be less than 0. So we should always try to break down this source term in such a way that it can be represented as SC plus SP into TP, where SP could be negative. So you can take any example of a nonlinear equation, try to break it down in such a way that the SP is negative and the multiplication SP TP is there, and there are no higher powers of TP. Otherwise, that would be a nonlinear problem again. And with this, I would conclude this lecture and also this lecture series. I think that this is a perfect time to stop the lecture series as well, because we have looked through a lot of variety of problems. We started with conduction, introduced the convection, introduced the pressure gradient, and then introduced the time derivative. So in a way, we had started from almost nothing, and I've tried to walk you through all these steps to arrive at the unsteady Navier-Stokes solutions. So hopefully you have enjoyed this lecture series, and I'm expecting that people in the future would be benefited from it as well. I'm very grateful to each and every one of you who have provided any kind of feedback on the lectures throughout this entire session, because that has really helped me to provide you the content that you are looking for. And I'll try to keep providing this content as well. So in the next few days, I'm planning to start a different course. So you'll hear about it sometime in maybe a week or so. But I hope that these 20 or so lectures, they have improved your understanding of CFD, and now you probably can call yourself a little bit more than a beginner in CFD. In case of any questions, you can always email me. My email ID is provided in the description, and I'll try to help you out in the best possible way. Again, a big thank to every one of you who have watched these videos and have learned anything from it. So until the next time I see you, bye-bye.